Welcome to the course on two-dimensional signal processing, principles and practices. We had done the 2D Fourier analysis. As a part of 2D Fourier analysis, we'll be looking at discrete Fourier transform in 2D. Before going into the 2D discrete Fourier transform, we'll look at the 1D DFT, how the signals are being looked at in the frequency domain. After knowing about this basics of 1D DFT and how we can use this in 2D DFT and how the frequency spectra of 1D DFT is helpful in visualizing the 2D DFT. So coming to the 1D DFT, this DFT we know that it's going to be a sampled version of DTFT, a discrete time Fourier transform. This we are talking about 1D, so it is the time is not dropped, it is DTFT here. So this DTFT, what we know is having the continuous omega, in which if we compare this DTFT and DFT, DTFT have this continuous one and DFT would be the sampled version of this DTFT. So the continuous frequency which is converted into discrete values in the DFT. So we will look at this in the spectra point of view, and one example of DTFT we have drawn and we have also done in the MATLAB code examples, and we had seen the continuous spectra. So that continuous spectra is sampled at a certain values, then you would obtain this DFT. So what does it mean actually that here? So the DFT is obtained by simply discretizing the frequency variable omega in the DTFT equation, where omega is 2 pi k by n. So this omega, x of omega or x of e power j omega, what we had for the DTFT equation. So both are valid notations and equal to n is varying from minus infinity to plus infinity in the summation x of n e power minus j omega, and this omega is continuous in case of DTFT. So this is sampled using this 2 pi k by n, where k is 0 to n minus 1, where k is also called the bin index, actually the harmonic or DC or fundamental, whatever depends on the value of k. K represents 0. Bin index 0 is DC value and 1 is fundamental. If k equal to 2 is second harmonic, and so on. So this is discrete version of the, if we substitute this omega equal to 2 pi k by n, then the discrete version of DTFT can be obtained, which is nothing but the DFT. So we'll look at DFT in detail. So that is also in the DFT converts this finite length discrete time sequence. That is the sequence is finite length, we should note it down. It's not in the case of DFS, which is pattern repeating, into a finite set of frequency domain samples. So finite set of time samples are mapped to finite set of frequency domain samples and are converted into frequency domain samples of finite set. So this can be viewed as we said, that it can sampled version of this. So both time and frequency representations are discrete and finite. So that's the thing which needs to be noted in case of a DFT. So now the DFT analysis equation xk, that is the frequency domain equation, where k is discrete, but still we use this parenthesis because in this is representing the frequency domain. N is varying from 0 to n minus 1 summation x of n e power minus j 2 pi k n. So where k is varying from 0 to n minus 1, without giving this expression, this will not be valid here. K needs to be varied from 0 to n minus 1. So that means k is 0 representing the DC value, and then fundamental k is 1 and second harmonic k is 2, and so on. So for the case of the n point DFT, this is the n is varying from 0 to n minus 1. So there are n points which can be obtained here as well. K is also having n points. For the sequence, x of n has n points. Both the sides it has n points here. So DFT synthesis equation, once we have the coefficients, DFT coefficients, we can obtain the signal back x of n using this, the scaling factor 1 by n. K is varying from 0 to n minus 1 summation x of k e power j 2 pi k n by n. So you can note down the basis function. What we do here is that x of n is known. In that x of n, we take the basis function and we can expand this as cos 2 pi k by k n by n minus j sin 2 pi k n divided by n. So if we write it, and cos and x of n, sin and x of n are correlated in this, and finding the similarity similarity between x of n and cos 2 pi k n, similarity between xn and sin 2 pi k n. So if there is a similarity, then this summation results in a value that is depends on the similarity, or it results in 0. So the correlation between these two results in a value. So that's how we find that DFT. We take an example. Suppose a continuous time signal x of t. So you can note down this contains a 1 kilohertz and 2 kilohertz. It's this DFT coefficients, obtaining it and visualizing this, what is the representation it is giving in the frequency domain, will be demonstrated through this example. So 1 kilohertz is this frequency this signal contains, also 2 kilohertz frequency it contains, and this is sampled at 8 kilohertz. Suppose we express this in terms of sinusoidal signal, 2 pi 1000 t 0.5 sin 2 pi 2000 t plus 3 pi by 4. So this is a signal which is given in the continuous time. So we sample it putting this nt equal to nts. Okay, so ts would be 1 by 8 kilohertz, and we can get x of n from that. So before doing the sampling, we to find out this 8-point DFT, for example. So this can be any n-point DFT. The given example, we find this n is equal to 8, and then x of t. Before getting into the sampling, we just write this representation in terms of cos theta minus pi by 2, and this is cos theta minus pi by 2. So if you write it, this would be easy to correlate the results. That's why we are writing it. It's an intermediate step to visualize the output or comprehend the output what we get in the DFT as a DFT coefficients. So here cos 2 pi and t minus pi by 2, what does it represents, and this angle, what is it going to represent in the DFT coefficient, how it is going to be related. So then get the samples. This is a signal. The signal x of t is plotted, okay, and the sine wave which is part of it is also shown here, and the sine again 2000 t is also shown here. So this summation of these two sequences 1 and 2 results in x of t. And now we take the sequence and sample it. So 2 pi 1000 t, 2 pi 1000 nts, 1000 nts. So here ts is taken to be 2 pi 1000 n, and this is 1 by 8000. So t is 8 kilohertz. So we get this expression through that. Simplifying it, we get sin 2 pi n. Similarly here 2 pi n by 4, this will be 2000, and by 2000 by 8000 we get this as 1 by 4 and 3 by 4. So this is the sampled sequence, and we get the samples from it, and these are the samples, 8 samples obtained through this by varying n equal to 0, you get the sample n equal to 1, 2, 3 and so on up to 7, 0 to 7 we get the samples. And once we have the samples ready, then we can apply or put it in the DFT equation, which is known. What is x of n? For x of k equal to 0, we will compute that. This is the plotted sequence of x of n, that is the samples what we got it from the sequence. So this sequence was obtained from the signal which we have the continuous time. So these are the samples of that sequence. So now applying in the DFT equation, so k equal to 0. So we put k equal to 0, so we get the expression as here. This would be 0, and so you will get the summation only from 0 to 7 samples varying it. So if you add over a period of this 0 to 7, so this is going to be 0. This is resulting x of 0 is 0. So representing that the DC here, instead of k equal to 1, we had given is this k equal to 0. So DC component is absent. K equal to 0 represents the DC. So obvious that from the signal what we had taken, it has 1000 hertz and then 2000 hertz. So 1k and 2k, it doesn't have any DC component. So it is showing it clearly here in the x of k equal to 0, this is 0. And similarly, if we compute x of 1, that is k equal to 1, and expand this equation for n values, substituting n values, the samples are all the samples we have 8 samples, and compute these values, that's giving to 4 angle minus 90 or 0 minus j4. This results some value, that is the correlation of this with k equal to 1 is giving you some value. That means there is a fundamental, the presence of this is shown k equal to 1, and if we make it in magnitude and angle, 4 minus 90 degree. And what is the for a value for k equal to 2, that is second harmonic? In that we get the expression as k equal to 2 and vary n and substitute the values of x of 0, 1, 2, 3, all of them together and sum it over. then get 1.414j or 1.414. This is giving 2 angle 45. X of 2 is this value. So now presence of fundamental is shown and second harmonic is shown. Yes, in the example taken, fundamental and second harmonic 1000 Hz and 2000 Hz are there. And we also compute the k equal to 3, 4, 5 and 6, 7 up to 7 and see the results also. For k equal to 1, what we did here is the signal, and k equal to 1, the fundamental sine wave and fundamental cosine. This is fundamental sine and fundamental cos. Okay, that is cos sine 2 pi k by n, sine 2 pi k by n, and this is cos 2 pi k by n. So k is 1 here, because this k is 1 and this k is 1. So if we correlate this sine and input, and we correlate this cos and this input, that's what we do in the DFT equation. And if these two are having the similarity, then it gives the value which is the presence of the fundamental. And similarly for k equal to 2, we can see that within the 0 to 7 points, it is completing the sine has 2 cycles. Okay, so, and then cos has 2 cycles, k equal to 2. So when this is cos, this is sine here, again 2 pi k by n, where k is 2, and here cos 2 pi k by n, where k is 2 here again. So we correlate it with the input signal, this second harmonic components, and finding whether there is a correlation or not. If there is a similarity, then it would result in a value which we had got for k equal to 2 as well. So that means the presence of second harmonic. And the case of k equal to 3, so you can see that sine wave and the cosine wave completing 3 cycles here within the sample period. So that's within the n points we have taken. So this one again correlating the sine and cos with the input signal. So we get the correlation coefficient as this value, which is the presence of harmonics. So now we'll see for k equal to 3, we have computed 1 and 2. K equal to 3 results in 0 because the input signal doesn't have the third harmonic. Okay, so finding this k results in 0. So that correlation would be 0. This is the absence of third harmonic. And k equal to 4 is also giving that k equal to 4, we are correlating with the input signal. So it also results in 0. K equal to 5 is also resulting in 0. And then k equal to 6, we have some value getting here. And it does mean this here, it is a 6th harmonic. Let us see, but in our input signal, there is no 6th harmonic, only 1 and 2 were present. And 7 is also having some value. Okay, so what are the 6 and 7 which is not available in the case of input signal? So now, and also we will interpret what is this 2 angle 45 and minus 45 or 4 angle 90. So now taking the spectra here, 0, we have just plotted the magnitude of this 0, and this is 4, 2, 3 and so on. So from 0 to 7 what we had obtained, and this phase spectra we get, this is going to be 0, 1, 2, 3, and it has minus pi by 2 and plus pi by 2 here. This is pi by 4, and here is again minus pi by 4 and plus pi by 4. So this is what the angle representation of each bin index k, and similarly the magnitude representation. So we got 4 here. What does it mean to get 4 in the fundamental? Our fundamental amplitude was 1, sine is 1 fundamental, and second harmonic had 0.5. So how do we interpret the magnitude spectrum with the original signal present in it? So this 4 is the fundamental, so 2 into n, that is going to be 4 into 2 by n is 8, so we get 1. So this is the original amplitude of the signal which is present over here. Similarly for k equal to 2, what we get is 2 into 2 by n, 2 by 8, that is going to be 0.5. So this is the 0.5 second harmonic which the original amplitude was. So this is how the obtained magnitude is multiplied by the 2 by n for the harmonics. This is valid only for the real signals, and the 2 by n, so get the original amplitude 1 and 0.5. What about the phase? Phase for the k equal to 1, there was no phase, but it is showing minus pi by 2. If you look at the representation in the few slides back, that we had done the cos of 2 pi 1000t minus pi by 2. So this 1 is representing the fundamental minus pi by 2, that pi by 2. This phase is with respect to the fundamental cos. And similarly second harmonic, which is having 3 pi by 4 minus pi by 2, that's resulting in pi by 4. This is the one for the second harmonic phase. So that is with respect to the cosine fundamental. So the phase spectrum should be interpreted with the cosine fundamental. And similarly, and now coming to 3 0 harmonic absent, and 4 is 0, 5 is 0, 6, what is that? 6 here and 7 here. So here what is happening, there is a complex conjugate. If you observe that 2 and 3, and these two are complex conjugates. So 1 and 7 are related. 7 is complex conjugate of 1, and 6 is complex conjugate of 2. So, and 5 is complex conjugate of 3. Here it is 3 0, so it is not showing it, and it's going as a 0. But so this is n is 8 and n by 2 is 4. So up to 0 to n by 2, samples are whatever we get in the frequency domain are independent terms, called independent terms. Yes, we need to, this is really representing the original signal what is present here. Here what we get at 5, 6, 7 are the complex conjugate of this. So though we didn't have 5 and 6, 7. So 6 and 7 are present over here. 6 is not there in the input signal. This is simply complex conjugate. This information is redundant information which is not required, or which is not giving any additional information about the signal. 6, what we say is same as 2, but complex, the conjugate of this value. So magnitude is looking same, but if we take the phase, this we can see the two of them. This is pi by 4 and this is minus pi by 4. Similarly, these two 1 and 7. So the interpretation should be, so 0 to n by 2 samples are the terms which you obtained in x of k are independent, and n by 2 plus 1 to n minus 1 samples what you get or the x of k terms are the complex conjugate of these terms. So this doesn't give any additional information. So it is sufficient to just calculate the DFT for 0 to n by 2 samples of k varying. So this is how it should be interpreted with the original sequence. And if DC is absent here, if DC is absent, then it is giving 0, but DC is present, that should be the DC value into 1 by n, the scaling factor, to get the original DC value. Okay, so and if suppose it is 2 resulting in 2 into 1 by n, that is 2 by 8, that 1 by 4 should be the DC value. So that's how DC value should be interpreted. So these are the spectral representation, and we can split them into real and imaginary part and plot this with respect to k as well. So real k will show the event symmetry, and the imaginary spectrum will show the x of k of the imaginary part of it would show the odd symmetry. So this is another way of representing it. Now coming to the important property of this DFT, that is symmetry, which is for real sequence, x of k is x conjugate n minus k. So that's how we get, if it is 1 and 8 minus 1, x conjugate 7. So x of 1 equal to x conjugate of, that's how we get it there in the spectrum. So 2 would give in 6, x of 2 results in x conjugate 6. So this is how these are symmetric, or these are equivalent. These are complex conjugate of 6 is complex conjugate of 2 and 7 is complex conjugate of 1. So first n by 2 terms are independent, that is 0 to n by 2 terms, and the remaining terms are not providing any additional information about the spectrum now. And the analysis frequency which we are interested in, so the sampling frequency Fs is related by f into n, and k is bin index. If I am interested in 50 Hertz, then that is going to be a fundamental, and Fs you can fix, depends on if n may be 128 or 8 or something, then Fs is going to be 6400 Hertz. So we can fix this sampling frequency accordingly, depends on the analysis frequency. And if you have this Fs by n, that is called the resolution in the spectra. So where k equal to 1, k equal to 2, 3, 4, in between there is an Fs by n present in it. So k 1 and 2, there is a Fs by n frequency between this k 2 minus 1, 3 minus 2, and so on. So it's linear, x of n, and can be represented with two signals x1 and x2. If you take the DFT of the individual, or sum x1 and x2 and take the DFT of the summed sequence, will be equal. It's also, if you multiply by a scaling factor a and b, that will also result in a and b here. And the case of DFT magnitudes, as I said, this is for kth harmonic, it should be multiplied by 2 by n, and to get the actual amplitude. For the case of DC, you have to multiply it by 1 by n to get the actual amplitude. And the frequency axis, the frequency spacing, or the resolution, we call it as Fs by n. So shifting theorem is very much useful. Also, that is one of the properties. If you know the DFT of this sequence x of n, that is x of k, and if you shift it left or right, x of n plus 3 or n plus k or n minus k, depends on that shifting. If you want the DFT of the shifted sequence, so that needs to be multiplied by e power j 2 pi k n by n with the known DFT, which is the not shifted sequence, that is x of n, whose DFT. So the shifted sequence is x of k and e power j 2 pi k n by n. So this k is the bin index. This is valid for all the k values from 0 to n minus 1, but the n represent here is nothing but the shifting. It is x of n plus 3 or n minus 3, what is not. So this one shifting the sequence will only affect the phase of the DFT, not the magnitude spectrum. Our magnitude will not be affected, and only the phase would be multiplied by this. So let's see the example of x of n, the sample sequence which we had considered for DFT, and then we get this x of n plus 3. There is ahead of it, the shifting it n plus 3. So you can see that 0.35 has gone to this minus 3. So this sequence, what's the DFT? For this sequence, we have already obtained the DFT. Suppose k equal to 1. And in this case, what we obtained is in the previous example that 4 angle minus 90, that is 4 e power minus j pi by 2 or 0 minus j4. So for the shifted sequence, for n equal to 3. So here we have to put that n is 3 positive if it is the left shift. If it is right shift, then it is going to be minus. Okay, so e power j 2 pi k, n is 3 by 8, which results in, so this is x of k, and we are multiplying through this with the factor, and we get this as 4 e power j pi by 4, which results in 4 angle 45. The previously it is 4 angle minus 90. You can see the angle difference minus 90 to 45. The phase shift has contributed here. So this is about the shifting theorem, and the shifted theorem helps in finding the DFT of the shifting sequence without computing it again by knowing the unshifted sequence DFT. Okay, this is what is helpful in the sliding DFT and so on. And we'll consider this DFT as a linear transformation, like so can we move from one plane to the other. So here a DFT of a sequence x of n is the DFT equation. So what we try to do is this e power minus j 2 pi by n, that we are replacing with wn. W suffix n here is e power minus jn. So we just replace this factor, that is called the Tudel factor, w suffix n kn. This kn is maintained as such here, and only this is called. So now looking at the x of k, everything here, this x of n equal to this in the IDFT also, e power j minus j 2 pi k by n. This is with the minus sign is wn minus kn. So you can see the Tudel factor gets replaced here. So this is x of k. So in the IDFT as well as in the case of DFT. Before getting into the transformation, so let's also know the computational complexity. So just aware of the computational complexity in the endpoint DFT. So using this equation, it's for a single bin computation, suppose k equal to 1, 0 or something, that what we had done already. So we will have to sum the signal x of n and its multiplication with this factor complex at least n times. So that's why n complex multiplications are required for one computation of k. And additions, you have to multiply and add it for n minus 1 times, isn't it? So n is varying from 0 to n minus 1. So the complex additions required here is n minus 1. This is for one computation of k value, k one bin index. It can be, we have to do it for the DFT computation from 0 to n minus 1. So in that case, it should be performed for n times. So k is also varying from 0 to n minus 1 to obtain all the bin indices. If you want only one bin index, this is the complexity using the DFT. And DFT also, this n can be even or odd. It doesn't matter in even or odd in the case of DFT. And for n bin computation, this is going to be multiplied by n. So that's why n into n, you get n square complex multiplication, whereas n minus 1 additions also multiplied by n. So that's for n times. So n into n minus 1 complex additions. So this is the complexity of the DFT. And let us also explore the further developments of the algorithm, how this computational complexity is getting reduced in further DFTs and the variants of this DFT, and in FFT and some other in 2D DFT also. And when we perform this 2D DFT using the 1D DFT, and what are all the, how can we reduce this complex multiplications and additions or the computational complexity, because these multiplications are costly in the DSP processes. So now using this DFT equation, let's find the transformation here. So for suppose x of n, the vector, the samples what we had, suppose in the previous example there are 8 samples. This is 8 samples, 0, 1, 2, 3, put it as a vector. So this order of this vector is, there is n rows, n cross 1 or 1 cross n if you alternate it in this. So it will have n samples. So this is x of n. And similarly, this is mapped into x of k in the frequency domain, where you would get k is varying from 0 to n minus 1, 0, 1, 2, 3 up to n minus 1. This is x of k. This is another vector which is of the dimensions same, like n cross 1 or 1 cross n, depends on the way in which we write. So there are n samples in it, and this is also a vector. So now getting xk from xn or getting xn from xk, what is the transformation needs to be used? That's what we are saying is a linear transformation. So we write with the in between, if we expand this sequence, like for k equal to 0, so x of 0, what we had is this is 0 and this is x of 0 plus x of 1 plus x of 2 and up to x of n minus 1. Okay, and if we put as x of 1, this is x of 0 plus x of 1 plus x of 2. In between you will have this k equal to 1 factor, that is e power minus j 2 pi, n is 0, this is n 0, and here you will have e power minus j 2 pi 1 by n and minus j 2 pi by n into 2 and so on. So you would get this. So if you keep expanding this x up to n minus 1, so you can see this can be written as only the matrix. If you take that out, 1, 1, 1, that's 1 is coming over here, and these are the factors, the Tudel factors Wn are collected from 0 to n minus 1. So that's how you get this up to n 0, and you can see this is 1, this is going to be 0, 0 and 1 n equal to 0, and here you get e power minus j 2 pi by n, and second one is e power minus j 2 pi by n. So these factors are collected and called as a Tudel factor matrix, and this goes up to n minus 1. And similarly, if we compute this x of 0 for all the values of it, this will be 1, and whereas the next column would compute up to n minus 1. So this is how it goes up to n minus 1 to n minus 1. So this is called the Tudel factor matrix. Once we obtain this Tudel factor matrix, which helps in this transformation from one domain to another, either to go into the frequency domain or to the time domain. So this vector is n cross n, and the e power minus j 2 pi by n, that is going to be e power wn, w suffix n, and it's into 2 is get a square, and here power n minus 1 is that whole power n minus 1. Similarly, it varies in other factors. So this is called the Tudel factor matrix, and this matrix has some properties. Also, when we want to obtain the frequency domain samples x of k, the spectra is equal to multiplying this wn into x of n, the input sequence, the vectors, the samples what we had, and xk equal to the multiplication of wn into xn. So this is the transformation matrix which is used to move from one to another. This is for getting x of k from x of n. And this matrix is a matrix of linear transformation, and this is a symmetric matrix. You can see that here, and this and this one and this one. So you would have the symmetric matrix. Also, this has certain properties, and we'll see them. And to get x of n from the case of frequency domain samples to time domain samples, in that case, this needs to be taken wn inverse should be taken, because x of k is obtained by multiplying the two wn and xn. So x of n can be written as 1 by n wn complex conjugate. So wn inverse is 1 by n wn complex conjugate. The wn is complex conjugate. What does it mean? Here is a complex conjugate transpose. Okay, that's a complex conjugate transpose. So this would also be, when you multiply, because it's a complex conjugate transpose, the property of this Tudel factor matrix can be wn into wn star would give n into identity matrix in. that is the n cross n matrix. And then Wn is the unitary and orthogonal as well. So if you take the unitary matrix, in that Q inverse equal to Q star, so that in complex conjugate is inverse. And in case of orthogonality, and Q into Q transpose is IR, Q transpose Q is equal to I. In that case, Q inverse is Q transpose. So that's how this dual factor matrix inverse is obtained by complex conjugate and transpose. So this is both unitary as well as orthogonal. So by going through the example, a simple example using this transformation, take a 4 samples here. We'll find out the 4-point DFT. So in that case, first we have to make the dual factor matrix of n 4. So 1 1 1 1, it stops with 1 2 3 and 1 2 3 here, 4 6 and 9. So we can refer to this previous how do we construct up to n minus 1 into n minus 1, that is 3 into 3 here is going to be 9. Okay. So obtaining these values, because W4 equal to here e power minus j 2 pi by 4, that's minus j, and minus j square is this, and the minus j cube is this. So here, so likewise we can substitute these values. So we get the matrix as this 1 1 1, this is minus j this, and this is minus 1 j and so on. So what we get is the dual factor matrix, and multiply the samples x of n, that what we had 4 samples, obtain the spectrum 6 minus 2 plus 2j minus 2 minus 2j minus 2 minus 2j. So multiplying it simply, and for computing the IDFT from the spectrum, so we take this, the values which needs to be here, yeah, this one, to obtain it, this is a transpose, the complex conjugate transpose, that is the inverse, and 1 by n is the 1 by n, Wn inverse is this matrix. This is simply the complex conjugate matrix of W4, and take the x of k samples and multiply them, you get the samples 0 1 2 3 here. So this is how the transformation simply using the dual factor matrix can be done. But if the order increases, the dual factor matrix order increases, it would be very tedious to compute the dual factor matrix and go to the real computing that DFT in case of real time sequences. So what we had seen in this one-dimensional discrete Fourier transform, how do we interpret the magnitude and phase spectrum using this 1D DFT, and the details, the basics of this 1D DFT, as well as how do we look at this DFT as a linear transformation with the help of the dual factor matrix. We had done that, and with an example, and this dual factor matrix can be used if the order of the sequence is less, that in the real-time sequences you will be having the number n more and more, then it would be difficult to find this dual factor matrix still and then compute the DFT. So there are variants for it, and to solve these problems, and we will extend this 1D DFT to 2-dimensional DFT, and how do we obtain this 2D DFT from the DFS and so on in the next lecture. Thank you.